After studying this module, you shall be able to know about free energy functions, that is Gibbs free energy and work function, know the dependence of Gibbs free energy on temperature and pressure, learn about Gibbshelmholtz equation, learn different Maxwell relations, derive Gibbsduhem equation and determine partial molar volume through intercept method. Thermodynamics is used to determine the feasibility of the reaction, that is, whether the process is spontaneous or not. It is used to predict the direction in which the process will be spontaneous. Sign of internal energy alone cannot determine the spontaneity of a reaction. The concept of entropy was introduced in the second law of thermodynamics. Whenever a process occurs spontaneously, then it is considered as an irreversible process. For such a process, the entropy change of the universe is positive. The change in entropy of universe is the sum of the entropy change of the system and the surroundings, that is delta S system plus delta S surroundings. It serves as a criteria of spontaneity of a reaction. If the total entropy change of the universe is positive, then the process is considered to be feasible. If the total entropy change is zero, then the system is considered to be in a state of equilibrium. Thus, for determining the feasibility of the reaction, the entropy change of the system as well as the entropy change of the surroundings should be known. But the entropy change of the surroundings is not easy to determine. For most of the spontaneous processes, it is observed that the system either tries to attain the state of minimum energy or maximum entropy. Thus, it is necessary to define a new function which takes into account both the properties, that is energy and entropy. Gibbs free energy G is a function that takes into account the effect of both the energy change as well as the entropy change of the system. Now we shall have a look at some free energy functions. Two functions which define the effect of entropy as well as the energy are work function abbreviated as A and the free energy abbreviated as G. These functions are defined by equations. Work function A is equal to U minus Ts or A equals to E minus Ts. This is our equation 1. Free energy G is equal to H minus Ts. This is our equation 2. Since H, U, T and S all are state functions, that is they depend on the state of the system, therefore G and A must also be state functions. Considering the work function at two different states but at the same temperature, then we get A1 equals to U1 minus Ts1 as our equation 3 and A2 equals to U2 minus Ts2 as our equation 4. Subtracting equation 3 from 4, we get A2 minus A1 is equal to U2 minus U1 minus T into S2 minus S1, or delta A equals to delta U minus T delta S. This is our equation 5, where delta A stands for change in work function, delta U stands for the change in internal energy and delta S stands for the change in the entropy. Since delta S equals to Q reversible by T, substituting this in equation 5, we get delta A equals to delta U minus Q reversible as our equation 6. From the first law of thermodynamics, that is delta U is equals to Q plus W, we get W reversible is equal to delta U minus Q reversible. This is our equation 7. If the system does the work, then the work will be negative. Accordingly, minus W reversible is equal to delta U minus Q reversible. This is our equation 8. On comparing equations 6 and 8, we get minus delta A equals to W reversible. This is our equation 9. Here, W is the maximum work done by the system. Thus, decrease in work function increases the work done by the system. Therefore, the function A is regarded as the work function and is also known as Helmholtz free energy. Similarly, considering the change in free energy by making use of equation 2, we get G2 minus G1 is equal to H2 minus H1 minus T into S2 minus S1, or delta G is equal to delta H minus T delta S. This is our equation 10. Also, the change in enthalpy at constant pressure is known as equation 11 as delta H is equals to delta U plus P delta V. Substituting equation 11 in equation 10, we get delta G equals to delta U plus P delta V minus T delta S as our equation 12. Using equation 5 in equation 12, we get delta G equals to delta A plus P delta V as our equation 13. Substituting equation 9 in equation 13, we get delta G equals to minus W plus P delta V, or minus delta G equals to W minus P delta V. This is our equation 14. In the equation, P delta V gives the work done by the gas on expansion against constant external pressure P. Thus, in equation, minus delta G gives the maximum amount of work done by the system other than the work obtained due to change of volume at constant pressure and temperature. But the amount of work done due to change of volume is W minus P delta V equals to minus delta G. This is our equation 15. The term G is known as Gibbs free energy. Now we shall see the effect of temperature and pressure on free energy. Considering the equation 2, we have G equals to H minus Ts. Also, H is equal to U plus PV. This is our equation 16. Substituting equation 16 in equation 2, we get G equals to U plus PV minus Ts as our equation 17. Differentiating the equation, we have dG equals to du plus pdv plus vdp minus tds minus sdt as our equation 18. For infinitesimal small change, the first law equation can be written as dq equals to du minus dw as our equation 19. As minus dw is equals to pdv, substituting this in above equation 19, we get equation 20, dq equals to du plus pdv. Making the use of equation ds equals to dq by d, or tds is equal to dq, which is equal to du plus pdv as our equation 21. Combining equation 18 and 21, we get dg equals to vdp minus sdt as our equation 22. The equation gives the change in free energy on variation of temperature and pressure. If the pressure of the system is kept constant, then dP is 0. Thus, equation 22 becomes dg equals to minus s dt as our equation 23. Rearranging the equation, we get dg by dt at constant pressure equals to minus s. This is our equation 24. Similarly, if the temperature of the system is kept constant, then dt is 0 and equation 22 becomes dg equals to V dP, or dg by dP at constant temperature is equals to V. This is our equation 25. Now we shall have a look at the Maxwell's relations, the expressions or equations which relate internal energy U, enthalpy H, Helmholtz free energy A and Gibbs free energy G with parameters like entropy, pressure, etc. are called Maxwell's relations. Some of these are: number 1, du equals to TdS minus PdV. Number 2, dH equals to TdS plus VdP. Number 3 equals to dA equals to minus SdT minus PdV. Number 4, dG equals to minus SdT plus VdP. If the volume of the system remains constant, that is dV equals to 0, then equation 1 becomes du by ds at constant volume equals to T as our equation 26. If the entropy of the system does not change, that is ds is 0, then equation 1 becomes du by dV at constant entropy equals to minus P as our equation 27. Now on differentiating equation 26 with respect to volume, keeping entropy as constant, and differentiating equation 27 with respect to entropy keeping volume constant, we get from equation 26 we get d square u upon ds dv equals to dt by dv at constant s. This is our equation 28. From equation 27 we get d square u by ds dv equals to minus dp by ds at constant volume as our equation 29. On comparing equation 28 and 29, we get dt by dv at constant s equals to minus dp by ds at constant v. This is our equation 30. Similarly, by following the same procedure, some relations were also derived as dt by dp at constant s is equal to dv by ds at constant p as our equation 31. ds by dv at constant t equals to dp by dt at constant v as equation 32. ds by dp at constant t equals to minus dv by dt at constant p as our equation 33. The relations are known as Maxwell's relation. Some more relations are du by ds at constant v equals to dh by ds at constant p from 1 and 2 as our equation 34. Similarly, from 1 and 3 we have du by dv at constant s is equals to da by dv at constant t as our equation 35. From 2 and 4 we have dh by dp at constant s is equals to dg by dp at constant t as our equation 36. And from 3 and 4 we have dA by dt at constant v equals to dg by dt at constant p as our equation 37. Some relations are also derived as follows. Helmholtz free energy, that is the work function A, is given by A equals to E minus ds. Differentiating gives dA equals to dE minus TdS minus S dt. But the combined first and second laws of thermodynamics reads TdS equals to dE plus P dV. Therefore, dA is equals to minus S dt minus P dV. As A is a function of t and v, we have dA equals to dA by dt at constant v dt plus dA by dv constant t dv. On comparing the coefficients of dt in the above two equations, we get dA by dt at constant volume equals to minus S and dA by dV at constant temperature equals to minus P. Now we shall see the Gibbs-Helmholtz equation. The variation of Gibbs free energy change with temperature is known as Gibbshelmholtz equation. This relation is derived as follows. Taking equation 24 as dG by dt at constant pressure is equals to minus S. For a small change from one state to another, the above equation can be written as d delta G by dt at constant pressure is minus delta S. This is our equation 38. Now taking the expression of Gibbs free energy, that is G equals to H minus Ts, differentiating it keeping the temperature constant, we get delta G equals to delta H minus T delta S as our equation 39, or delta S is equals to delta H minus delta G by T. This is our equation 40. Substituting this in equation 38 and then on rearranging, we get d by dt of delta G at constant pressure minus delta G by T is equals to minus delta H by D. This is our equation 41. From differential calculus, we have d by dt of delta G by T equals to 1 by T into d by dt of delta G minus delta G by T square. This is our equation 42. So equation 41 can be written as T into d by dt of delta G by T at constant pressure. Thus, we can write this as T into d by dt of delta G by T at constant pressure is equals to minus delta H by D. This is our equation 43, or this can also be written as d by dt of delta G by T at constant pressure is equal to minus delta H by T square. This is our equation 44 and is known as Gibbs-Helmholtz equation. It is valid for all processes which occur at constant pressure. The enthalpy change can also be calculated using this equation, provided that the values of free energy changes at two different temperatures are known. Now we shall learn about the partial molar properties. Some thermodynamic properties like entropy, enthalpy, internal energy, etc. are called as extensive properties because their values change by varying the mass of the system. In many thermodynamic equations, the change of state was due to the variation of temperature and pressure only. Accordingly, it was assumed that in the case of closed system, there is no change in the mass of the system, while in the case of an open system containing two or more components, the number of moles of various components can also be changed. In such case, the extensive property X must be a function of number of moles of various components of the system in addition to temperature and pressure of the system. Now we shall see the expression of partial molar quantity. Suppose the temperature of the system be T and pressure be P, and N1, N2, N3 up till Nj be the corresponding number of moles of the components 1, 2, 3 up to J. Thus, accordingly, the property X must be the function of temperature, pressure and the number of moles of various components of the system, that is, X is a function of T, P, N1, N2, N3 up till Nj. This is our equation 45. The total number of moles N is equals to N1 plus N2 plus N3 up till Nj. Thus, change in property Tx when the temperature, pressure and the number of moles change will be. This is our equation 46. This quantity dx by dni at constant T, P, N1, N2 up till Nj is called the partial molar property of the ith component. This is also represented as xi bar. Thus, the partial molar property may be defined as the thermodynamic quantity which shows that an extensive property of a solution or mixture changes with the change in the molar composition of the solution, while keeping the temperature and pressure constant. It is a partial derivative of the extensive property with respect to the amount of the component of interest. Each extensive property of a mixture has its corresponding partial molar property. Thus, for any component, say the ith component of a system, we have partial molar Gibbs energy as dG by dNi at constant T, P, N1, N2, N3 and so on as Gi bar, partial molar internal energy as du by dNi at constant T, P, N1, N2, N3 and so on equals to Ui bar, partial molar enthalpy dH by dNi at constant temperature, pressure N1, N2, N3 and so on equals to Hi bar, partial molar entropy ds by dNi at constant T, P, N1, N2, N3 and so on equals to Si bar, partial molar volume dV by dNi at constant T, P, N1, N2, N3 and so on equals to Vi bar. This is our equation 47. Now we shall see the physical significance of partial molar quantity. The quantity Xi bar represents the actual value of X per mole of the ith component of the system. This value may be same or different from the actual molar value X in the pure state. These two values, that is the partial molar value and the actual molar value, are same in case of the ideal systems. While in the case of non-ideal systems, the two values are different because of the interaction between the constituents. That is, actual molar volume value gets modified to partial molar value. This partial molar value may not be same throughout the whole solution, since the extent of interactions vary according to the amount of the constituents in the system. Hence, the partial molar value is dependent on the composition of the system. Therefore, the partial molar quantities are meant for the individual components of the system, but their values are not only dependent on the nature of the particular component in consideration, but also on the nature and amounts of the other components of the system. Now, taking some partial molar properties in detail in the next section. First, we have the partial molar volume. The partial molar volume of a substance, say the ith component in a mixture, is the change in volume per mole of the substance I added to a large volume of the mixture. In the case of ideal solution, the partial molar volume of the ith component will be equal to its molar volume in the pure state, whereas in the case of non-ideal solution, the partial molar volume is the molar volume actually occupied by the substance in the solution of known composition. The partial molar volume of the constituents of the mixture changes with the composition. As the partial molar volume is the actual molar volume of the component present in the solution of known composition, therefore, the total volume of the solution will be given as V total equals to N1 V1 partial molar plus N2 V2 partial molar. This is our equation 48. Now, we shall see the determination of partial molar volumes for a two-component system. The value of partial molar volumes of the components of the solution can be determined by various methods. A direct method to measure V1 Pm, that is the partial molar volume of the component 1, is to measure the volume of the solutions which is formed by adding different amount of component 1 in a definite amount of component 2. Then a graph is plotted between the volume of the solution and the amount of the component 1. At the given composition of the solution, the slope of the line at the composition gives partial molar volume of the component 1. But better method for determining the partial molar volumes is the intercept method. Now we shall have a look at the intercept method. Assuming Vm mix be the volume of the mixture consisting of total of 1 mole of the two components, thus we can write it as Vm mix equals to V upon N1 plus N2. In the above expression, V stands for the volume of the mixture consisting the amounts N1 and N2 of the corresponding components 1 and 2. Under constant temperature and pressure, the partial molar volume can be written as V1 Pm equals to dV by dN1 at constant N2, which can be further written as d by dN1 of N1 plus N2 into Vm mix at constant N2. After undergoing the differentiation, the expression becomes equal to Vm mix plus N1 plus N2 into dVm mix by dN1 at constant N2. This is our equation 50. Since the total mole fraction of the system is equal to 1, that is Chi1 plus Chi2 is equal to 1, thus the total molar volume Vm mix at specified temperature and pressure will be the function of only one of the mole fraction terms, that is Vm mix is function of Chi2. Taking differential of the above expression, we get dVm mix is equals to dVm mix by dx2 into dx2 as our equation 51. Now dividing the equation by dN1 and taking N2 be constant, we get d by dN1 of Vm mix at constant N2 is equal to d by d Chi2 of Vm mix into d by dN1 of Chi2 at constant N2. This is our equation 51.1. Since the mole fraction is given by Chi2 equals to N2 upon N1 plus N2, this is our equation 52. Thus, for the expression d by dN1 of Chi2 at constant N2 is equal to minus N2 by N1 plus N2 whole square as our equation 53. Substituting equation 52 in equation 53, we get d by dN1 of Chi2 at constant N2 equals to minus Chi2 by N1 plus N2 as our equation 54. Substituting the equation 54 in equation 51.1, we get dVm mix on dN1 at constant N2 equals to dVm mix by d Chi2 into minus Chi2 upon N1 plus N2 as our equation 55. Putting this expression in equation 50, we get V1 Pm equals to Vm mix minus Chi2 into dVm mix by d Chi2 as our equation 56, or Vm mix is equals to V1 Pm plus Chi2 into dVm mix by d Chi2 as our equation 57. Similarly, for the second component, the partial molar volume will be given by Vm mix equals to V2 Pm plus Chi1 into dVm mix by d Chi1 as our equation 58. The equations represent tangent line drawn to the plot of Vm mix versus Chi2, taking equation 57 with the intercept equal to V1 Pm, and accordingly the slope of the line is given by dVm mix by d Chi2. Similarly, the plot is drawn between Vm mix and Chi1, in which the intercept becomes V2 Pm and the slope is dVm mix by d Chi1. Both the equations given above represent a single plot because Chi1 plus Chi2 is equal to 1. This plot is shown in the figure given. The figure depicts the method of intercepts to determine the partial molar volume of components of a binary solution. In this figure, intercepts are V1 Pm at Chi2 equals to 0 or Chi1 equals to 1 and V2 Pm at Chi2 equals to 1 or Chi1 equals to 0. The equations 57 and 58 are valid for any extensive property Y that gives V, G, U, S, A or H of the mixture. Thus, the generalized equation is written as Ym mix equals to Y1 P1 plus Chi2 into dYm mix by d Chi2 as our equation 59, and Ym mix equals to Y2 Pm plus Chi1 into d Ym mix by d chi 1 as our equation 60. Now we shall see the determination of partial molar volumes for system containing more than 2 components. Suppose the solution is comprising of more than 2 components, let M, then from equations 49 to 54 we come to the conclusion that VIPM equals to Vm mix plus N total into dVm mix by dNi at constant Nj, where J is not equal to I. This is our equation 61. Vm mix is the function of chi 1, chi 2 up till chi m as our equation 62. dVm mix equals to summation over k not equals to I of dVm mix by d chi k at constant chi L, where L is not equal to k and I, into d chi k. This is our equation 63. Similarly, we have equation 64 and equation 65 as d chi k upon dni at constant nj, where j is not equal to I equals to minus chi k by n total. Now substituting equations 64 and 65 in equation 61, we get VIPM equals to Vm mix minus summation k not equal to I chi k into dVm mix by d chi k at constant chi L, where L is not equal to k and I. The equation 66 gives the partial molar volume in solution consisting of more than 2 components. Now we shall see the partial molar Gibbs energy. The partial molar free energy GIPM is the most important partial molar quantity in the physical chemistry. It is known as the chemical potential as in represented as dG by dNi at constant T, P, N1, N2, N3 and so on equals to Gi bar, which is equals to mu I. This is our equation 67. Thus, chemical potential is the change in the free energy of the system which results on the addition of 1 mole of that particular substance to a very large system such that the overall composition of the system does not change while keeping the temperature and pressure constant. Now, writing the free energy change by an infinitesimal amount, we have dG equals to dG by dt at constant P and N dt plus dG by dP at constant T and dP plus mu1 dN1 plus mu2 dN2 plus so on up till mu j dNj as our equation 68. In this, mu1, mu2 up till mu j are the chemical potential of the corresponding constituents 1, 2 and so on up till j. Assuming temperature and pressure to be constant, the free energy change will be given by dG at constant T and P equals to mu1 dN1 plus mu2 dN2 up till plus mu j dNj as our equation 69. That the system has definite composition having N1, N2 up till Nj moles of components 1, 2, 3 up till j respectively, then integrating equation 69, we get equation 70 as G as a constant T, P and N equals to N1 mu1 plus N2 mu2 up till Nj mu j. Thus, by looking at the above equation, chemical potential may be defined as the contribution to the total free energy of the system by 1 mole of each component of the mixture while keeping the temperature and pressure constant. And Gibbs free energy of the system is the sum of n mu terms of the individual constituent of the system. Now we shall see the Gibbs-Duhem equation. Chemical potential is dependent on the composition of the system. To understand this, take the total differential of equation 70 dG equals to mu1 dN1 plus N1 d mu1 plus mu2 dN2 plus N2 d mu2 up till mu j dNj plus Nj d mu j as our equation 71. Separating differential of chemical potential and differential of number of mole terms, we have dG equals to mu1 dn1 plus mu2 dn2 plus mu j dnj plus n1 d mu1 plus n2 d mu2 plus up till nj d mu j as our equation 72. But from equation 69 we know that at constant temperature and pressure dg at constant T and P equals to mu1 d mu n1 plus mu2 d n2 up till plus mu j d nj as our equation 73. Therefore, we have n1 d mu1 plus n2 d mu2 up till nj d mu j equals to 0. It is concluded that at constant temperature and pressure, the system has definite composition, that is summation nj d mu j is equals to 0. This is our equation 74 and is called as the Gibbsduhem equation. The significance of the Gibbsduhem equation is that the chemical potential of one component of a mixture cannot change independently of the chemical potential of the other components. For a two-component system, the equation can be written as n1 d mu1 plus n2 d mu2 equals to 0. On rearranging the equation, we have d mu1 equals to minus n2 by n1 into d mu2. This is our equation 75. Thus, by looking at the equation, we can say that the variation in chemical potential of one component of the system can bring the variation in chemical potential of second component of the system. Some important results obtained after Gibbsduhem equation are: if the number of moles of components of a system remain constant, that is, the terms dn1, dn2 up till dnj are 0, then the equation 5 becomes dg equals to dg by dt at constant Pn into dt plus dg by dp at constant Tn dp as our equation 76. But for closed system, it is known that dg equals to vdp minus sdt as our equation 77. Thus, by equating the equations of dt and dp in equations 76 and 77, we get dg by dt at constant p and n equals to minus s. This is our equation 78. And dg by dp at constant t and n equals to v. This is our equation 79. By the results obtained above, the variation of chemical potential with temperature and pressure can be obtained. Thus, these results are important. Now, we shall discuss a question. For an ideal gas undergoing isothermal reversible expansion, show that delta G equals to delta A. The solution is as follows. The free energy functions G and A are given by G equals to H minus Ts and A equals to U minus Ts. Also, enthalpy is given by H equals to U plus PV. Substituting this enthalpy in the expression for free energy G, we get G equals to U plus PV minus Ts, or this can be written as U minus Ts plus PV, or G equals to A plus PV. Thus, for the process, delta G equals to delta A plus delta PV. For an isothermal expansion of an ideal gas, we have delta PV equals to delta nRT equals to 0, as delta T is 0 for an isothermal process. This gives delta G equals to delta A. Now, we shall summarize what we have learnt in this module. The two work energy functions are free energy G equals to H minus Ts, work function A equals to U minus Ts. The expression for variation of Gibbs free energy with temperature keeping the pressure constant is dG by dt at constant P equals to minus S. Similarly, the variation of Gibbs free energy with pressure keeping temperature constant is dG by dP at constant T equals to V. Maxwell's relations are the expressions connecting internal energy U, enthalpy H, Helmholtz free energy A and Gibbs free energy G with parameters like volume, pressure, entropy, etc. Some of these are 1. du equals to TdS minus PdV. 2. dH equals to TdS plus VdP. 3. dA equals to dA minus SdT minus PdV. 4. dG equals to minus SdT plus VdP. Gibbs-Helmholtz equation is the variation of Gibbs free energy with temperature and is given by d by dt of delta G by T at constant pressure equals to minus delta H by T square. The quantity dx by dNi at constant T, P, N1, N2 up till Nj is called the partial molar property of the ith component. This is also represented as Xi bar. The partial molar volume is represented by VIPM equals to Vm mix minus summation K naught equals to I chi K dVm mix by d chi K at constant chi L not equals to Ki. Gibbs-Duhem equation is given by summation Nj d mu j is equals to 0.